Welcome to lecture number 27 of fuzzy sets, logic and systems and applications. Today we will be discussing the parameterized S norm operators, and here we have Dombey's class of S norm, Dubai's Praday's class of S norm and Jager's class of S norms. The parameterized S norm, we can call this as parameterized T co-norm. So, let us go one by one and discuss the first Dombey's class of S norm. So, if we have two fuzzy sets, let us say A and B with universe of discourse capital X. So, the Dombey's class of S norm is defined by this expression, where S lambda is the Dombey's class of S norm operator. So, S lambda of mu A of x and mu B of x, this is equal to 1 over 1 plus 1 over mu A of x minus 1 raised to the power minus lambda plus 1 over mu B of x minus 1 raised to power minus lambda whole raised to power minus 1 over lambda. So, this is defined by this, and the lambda values here will be in between 0 and infinite. So, as I have already mentioned that the S lambda of mu A of x and mu B of x here is basically termed as the S norm operator, Dombey's class of S norm operator applied on the two membership values, and these two membership values are from two different fuzzy sets whose union are to be found. So, here this has to be noted that normally we use S norm when we are interested in finding the union of two fuzzy sets. So, here also we take two fuzzy sets, and if we are interested in union of these two fuzzy sets, so we can either use the basic S norm, where we take the max, where we take just the union by taking max, but in parameterized norm we have the expression here which is given by Dombey's class of S norm, and Dombey's class of S norm as I have mentioned here, and this involves a parameter lambda, and this lambda will be in between 0 and infinity. So, let us take an example here where we have two discrete fuzzy sets A and B. You can see here discrete fuzzy set A is shown here and discrete fuzzy set B is also shown here. We are interested in the union of these two fuzzy sets A and B, and the discrete fuzzy set A has two elements here, discrete fuzzy set B also has two elements here, and both the elements you can see have the membership values for corresponding generic variable values. So, when we take the union of these two, we can use the S norm, and that too with the Dombey's class of S norm. So, when we use Dombey's class of S norm, we apply the expression that I just discussed, and this expression is nothing but the S lambda of mu A of x and mu B of x, which is equal to 1 over 1 plus 1 over mu A of x minus 1 raised to the power minus lambda plus 1 over mu b of x minus 1 raised to power minus lambda and then whole raised to power minus 1 over lambda. So, when we apply this expression for all possible pairs of the membership values of fuzzy set A and fuzzy set B. So, we see that the resultant fuzzy set which is here. So, the first term is like this, it is 0.709 oblique 1 plus 0.833 oblique 2. So, we have two terms and this basically is a fuzzy set of the resulting fuzzy set out of the union of fuzzy set A and fuzzy set B. So, we can clearly see that we had two discrete fuzzy sets A and B and both the fuzzy sets have two elements and hence the union of these two will also have two elements. So, here we take the union of fuzzy set A and fuzzy set B and this is what is resulting here as the fuzzy set and we see that when we take the parameter lambda is equal to 0. So, please note that we can take any value of lambda in between 0 and infinity depending upon our suitability or requirement. These values are used for finding the different sets of the union of the fuzzy set A and fuzzy set B. So, we see that when we take lambda is equal to 1, the resulting fuzzy set here we get as which has two terms and which has been shown here. And now, if we change the value of lambda to 2. So, let us see what happens. So, we see that when we increase the value of lambda from 1 to 2, the membership values of the corresponding generic variable values are reducing or I would say decreasing. So, when we take the union of fuzzy set A and fuzzy set B for the value of lambda is equal to 2, we see the fuzzy set which has the increased value of the membership for corresponding generic variable values. So, when we take the value of lambda is equal to 3, let us see what we are getting here. We again see that once again I would like to tell you that when we increase the value of lambda, the membership values are reducing. You can see here in the previous example where we took lambda is equal to 1, the union of the fuzzy sets A and fuzzy set B, we have the membership values that are reducing when we increase the value of lambda. So, for value of lambda equal to 3, here also we see the decrease in the membership values. So, we can say when we increase the value of lambda for the same set as input, the resulting fuzzy set will have reduced membership values of the corresponding generic variable values. Now, let us discuss the Dubais-Pradès class of S norm. So, here we have S alpha and this Dubais-Pradès class of S norm is represented by S lambda and on the same lines as we have discussed in the previous class where we took the Dombey's class of S norm. So, here we use S alpha. So, this is going to be equal to mu A of x plus mu B of x minus mu A of x into mu B of x minus min of mu A of x comma mu B of x comma 1 minus alpha. So, here we use alpha as the parameter and then this is divided by the max of 1 minus mu A of x comma 1 minus mu B of x and alpha. Please understand that the alpha takes the values anywhere from 0 up to 1. So, let us now take the same fuzzy sets as we have taken and in the previous example, and let us find the union of two fuzzy sets using Dubais-Pradès class of S norm. So, we have two fuzzy sets here, fuzzy set A and fuzzy set B. A is defined by this expression and B is also defined by here this expression. These two fuzzy sets are discrete fuzzy sets. So, when we apply the expression that I just discussed for S alpha, which is for Dubais-Pradès class of S norm. So, when we use this for finding the membership values of the resulting fuzzy set, which is out of the union of fuzzy set A and fuzzy set B. So, we are getting two terms here in the resulting fuzzy set. So, we see that we get two terms and these two terms will have its membership values for corresponding generic variable values 0.7 by 1 plus 0.8 by 2. So, here if we take union of these two fuzzy sets, we are getting a fuzzy set which will have two elements, which is shown here, and this is when you take the alpha is equal to 0.1. Similarly, when we increase the value of alpha, let us see what we are getting. So, when we take the union again of fuzzy set A and fuzzy set B, and here we get resultant of this union of fuzzy set, which is again a discrete fuzzy set which has two terms, and we see that there is not any significant change here in the membership values of the resulting fuzzy set, which is out of the union of fuzzy set A and fuzzy set B. So, here this case is when we have taken alpha is equal to 0.2. So, this result is same as the alpha is equal to 0.1. And then when we again go ahead and we use alpha is equal to 0.3, we see that again we do not see any significant increase in the membership values of the resulting fuzzy set. So, of course, here alpha is not playing a big role, or I would say alpha is here with the membership values of the fuzzy sets that we have taken, and it depends upon the combination of the membership values and then the alpha. So, here in our case, even when we increase the value of alpha, we see that we do not have any significant increase in the values of the membership of the resulting fuzzy set. So, this way even when we increase the values of alpha, we do not see any significant change. Now, let us discuss the another class which is Jaeger's class of S norm. So, we have for Jaeger's class of S norm for finding the union of the two fuzzy sets. So, by using this Jaeger's class of S norm, we can operate this Jaeger's class on any two membership value of the fuzzy sets that we are interested in finding out the union of. And if we have a fuzzy set A and fuzzy set B, So, we will have the corresponding membership values as mu A of x, mu B of x. So, when we apply Jaeger's class of S norm on these two membership values, mu A of x and mu B of x, and this will be equal to min of 1 and mu A of x raised to power w plus mu B of x raised to power w, and then whole raised to the power 1 over w. You can see here. Here w is a parameter of Jaeger's class of S norm, and this w is going to be in between 0 and infinity. So, the w can take any value in between 0 and infinity. Let us now understand this also, Jaeger's class of S norm also, by taking an example. So, here we take two discrete fuzzy sets A and B, and here we will be taking the union of these two fuzzy sets, and we will be using the Jaeger's class of S norm to find the union, and let us see what happens when we use Jaeger's class of S norm. So, we have two fuzzy sets as I mentioned, and when we take union of the fuzzy set A and fuzzy set B. So, obviously, the membership values of fuzzy set A, membership values of fuzzy set B we will collect, and then we will use Jaeger's class of S norm on these the pairs of the membership values that are coming from fuzzy set A and fuzzy set B. So, when we do that, we use Jaeger's class of S norm, we find another fuzzy set as a result, which will have two elements. So, one of the elements will be 0.8 by 1 plus 1.0 by 2. So, if we see here that when we take the union of fuzzy set A and fuzzy set B, we get another fuzzy set which is the resultant of the fuzzy set of the union of fuzzy set A and fuzzy set B. We have two elements in this fuzzy set, and this element has 0.8 as the membership value corresponding to the generic variable value as 1, plus we have 1 as the membership value corresponding to the generic variable value 2, and both of these have been plotted here you can see, and this is for w is equal to 1. So, w is an important parameter here in Jaeger's class of S norm, and when we change the value of w, let us see what happens. And obviously, as I mentioned, the w can be any value in between 0 to infinity. So, let us now use again both the fuzzy sets, and let us find the union of these two fuzzy sets A and B, and we take the value of w 2. So, w is equal to 2, we are going to get here some change in the membership values of the resulting fuzzy set, which is coming out of the union of fuzzy set A and fuzzy set B. So, we can clearly see that the values of the membership are changing as we are changing in w, means the values of the membership are reducing here. So, earlier we had 0.8 and then now we have 0.707 for the generic variable 1, when we have changed the value of w from 1 to 2. So, this means that when we increase the value of w, the membership values of the resulting fuzzy set are reducing. So, similarly, when we again take the value of W as 3. Here you can see the W is equal to 3. So, when we take W is equal to 3, again there is some decrease in the values of the membership of the corresponding generic variable values of the resulting fuzzy set, which is coming out of the union of fuzzy set A and fuzzy set B. So, this way we can say that we have the parameterized S norms. This is also called as T conorm. So, we can either say we can either call the parameterized S norm or parameterized T conorm, and we have 3 parameterized S norms as we discussed: Dombey's class of S norm, Dubais-Pradès class of S norm, and Jaeger's class of S norms. And let us compare these S norms for the parameters that are involved here in these 3 parameterized S norms. So, let us see what happens when we are increasing the values of lambda in case of Dombey's class of S norm, and alpha in case of Dubais-Pradès class of S norm, and W when we take the case of Jaeger's class of S norm. So, this we have already discussed, but I would like to just summarize and conclude here that you see when we increase the value of lambda here. So, we can see here this is for lambda is equal to 1, and then this lambda is equal to 2, this for the Dombey's class of S norm, and then when we take the lambda is equal to 3. So, you see the output. So, we see that the output, the resulting fuzzy set, that is out of the fuzzy set A union fuzzy set B. So, we see that as we increase the value of lambda, the membership values of the resulting fuzzy set for the corresponding generic variable values are reducing. So, this is very clearly visible, and when we see this in Dubais-Pradès class of S norm, here in Dubais-Pradès class of S norm we have alpha as the parameter. So, when we increase the value of alpha, we see that there is not much change, or I would say not a significant change in the output, even when we change the when we increase the values of the alpha. So, this is alpha is equal to 0.1, and then we have alpha is equal to 0.2, and then when we have alpha is equal to 0.3. So, here once again I would like to mention that we have Dubais-Pradès class of S norm, and here even when we increase the value of alpha, we do not see any significant change in the membership values of the corresponding generic variable values of the resulting fuzzy set, which is coming out of the union of fuzzy set A and fuzzy set B. Now, in case of Jaeger's class of S norm, on the again on taking the union, when we use Jaeger's class of S norm, we see that when we take W is equal to 1. So, we see that there is the decrease in the membership value. So, as we increase the value of W here, W is a parameter in Jaeger's class of S norm, we see that the membership values are decreasing. So, these membership values of the corresponding generic variable values of the resulting fuzzy set, which is coming out of the union of fuzzy set A and fuzzy set B. So, this way we have seen as to how the parameters of the parameterized S norms are playing an important role in the resulting fuzzy set. So, today we have discussed the parameterized S norms in detail, and in the next lecture we will be discussing the another topic that is fuzzy relation. Thank you.